Hi everyone, and welcome back to episode 5 of AI Unboxed. In today's episode, we are bringing together industry leaders for a panel discussion on one of the biggest challenges in AI right now: how to scale infrastructure to optimize performance. In this session, you'll hear real-world insights from leaders at Meta, Broadcom, and Dell as they share how they are scaling AI systems to meet growing demands and optimize results. If you're thinking about how to design, expand, or future-proof AI infrastructure, you're in the right place. We'll cover a lot today, and we want this to be interactive. That's why we have experts monitoring chat in real time. So drop your questions in the Q&A panel as we go, and we'll get to as many as we can. Take it away, Mike.
What's the best way to unlock the potential of your AI data center? Do you scale in to optimize resource utilization? Should you scale up to power high-performance training? Or perhaps you scale out to enable distributed AI workloads? In this dynamic panel, industry leaders come together to share their real-world insights on how they're scaling their AI infrastructure and getting the most out of their AI data center deployments.
Thanks everyone for joining. I know some of you are eating. Feel free to, try to enjoy the panel discussion as well as the food, right? So we'll do that. And the panelists don't need any introduction. They are really moving the boundaries of technology. This is what makes Silicon Valley, Silicon Valley. I'm so excited to be with my friends here on stage, right? So we are nicely set up. Ram and Joachim talked about the trends out there. So I thought we could use those trends and gather your insights and thoughts, right? All of you are really working on real hardware, software, hardware, co-design, integration. You have real insights. So I'm going to give you a broad platform for you to share some of the insights. So we'll start with, okay, let me bring up my list, right? So that I don't miss out anything, right? So we talked about backend networks training was the focus. And we are shifting. I mean, they're not quite correlated, but there is decent enough correlation about, inference picking up and AI finding its value with slowly, amount of data movement and front-end networks, right? And a couple of weeks ago, I saw a presentation at Meta that your back-end to front-end network connectivity, you started using more NICs than before, higher speeds and things like that. Maybe I'll start with you, Manoj. And do you see focus shifting to front-end? Not that we're forgetting back-end, but how do you see that?
Yeah, for sure, the focus is not going away from anything. It's just increasing more and more. Like what you talked about, I mean, just to put it in context, right? The amount of GPUs that we used in our use cases, a few years back when we started with Llama, where we started with a 2K and a 4K cluster, right? That could be fit into a single data hall. That quickly expands into that goes across the data center building, which will go to 24K. Try to bring multiple of them together within the region that we can take us to 100K. But what we are targeting is, let's say, million GPUs that are working on the job, right? To get to this kind of a scale, the number of GPUs that we install, deploy, and the number of GPUs that can go into a server keeps on increasing. Which brings us to the front-end network is basically, as we look at more and more flops, as we look at more and more scale-up and scale-out bandwidth increasing, all of this requires significant ingest also. So this is where the front-end continues to expand. That if you had 4 GPUs that are connected to a single OS instance from a single CPU, the front-end has to continue to grow up. So a few years back, storage used to be the leading use case for driving the bandwidth. Now we can easily see that AI continues to drive that bandwidth, and the use cases continue to evolve. And we were just joking before this panel, we got into the stage that 3 months back we got together at Keysight event, and I was thinking what would change in 3 months, and then I started going through each of those things in my mind, and everything is blowing up. The bandwidth that we need, the amount of infrastructure that we deploy, the power that we require for bringing all these things together, what we can put in a single data center is definitely going beyond the capacity. This is where the scale out or scale across the terminology, what we used to do within a data center is going to 5 kilometer, 10 kilometer, up to 100 kilometer of range. So the networking problem statements are varying and changing from front end to scale up to scale out. Scale up itself is an interesting topic, but I'll keep it for a discussion later. But for sure, all of these are expanding.
So looks like we need these events every 3 months just to keep it up, right? But coming to you, Joe, you are the pioneer on the storage side, right? There is a huge implication, especially when the focus is shifting to the front-end networks on how a lot of data in your cloud, a lot of data in locally is there, but across data centers that are remote, right? How do you see?
Data access. So the access of data only across the front-end network, I think, will change. So I think data will be accessed from other networks. I think data staging becomes important again. For 40 years, we've had concepts like, hierarchical storage management, still relevant. The ability to read and write tokens as the algorithms learn, critical. So how do you have agentic if it doesn't learn? How do you learn if you can't save information? We don't work that way. We save information in a variety of places. I think the AI systems are going to do the same thing. And as we adapt to the more heterogeneous cases, you will have to access data from everywhere, which means you're going to need intelligent components, like we heard about earlier, say, data processing units and even the GPUs themselves, organizing better ways to go after that data. I think the data is going to live at all of these scales. I think this kind of radiating out picture is very evocative of the complexity we're dealing with. And you're going to have to deal with data at every single one of these levels. And that's a shift in thinking, right? Because in the past, we thought of data as being over there on a special network with special protocols and special access. That's all going to have to change. MCPs are going to change it. The nature of the data used to train the AI, the rumination on the data and on the tokens you generate will change it. And all of that's necessary to have AI fulfill the promise of being able to do something useful for you beyond summarizing meeting notes. And the promise is there. The reality hasn't quite caught up, but AI is good for a lot of things today. For the big one for me, especially after listening to the agentic discussion this morning, is can I get a set of AIs to run my data center for me, ultimately? And in the meantime, can I extend operator span of control? And if I can beat this multi-layer scaling battle, maybe. And that's the challenge we're all going to face, because we're not going to be able to afford to run the networks required to both access the data and have the GPUs and CPUs communicate. We're just not going to be able to afford to operate it. Yeah. And when things go wrong, we're going to lose millions of dollars a minute of trying to fix it. That means we need automated systems to do fixes. So I don't, you're going to get so you've got a physical infrastructure issue. You've got a multiple layers issue. You've got a how do you run the thing issue, coupled to multiple scaling domains all at once. It's wild. It's bigger than anything that I've ever seen in the industry. It's the biggest transformation for networking. It's bigger even than the internet transformation that began to happen, in the 90s when I was still a physicist.
Thank you. So hopefully the agents run while I'm sleeping, and when I can't move fast enough, rest of the things I'll continue to run the network.
Right? You're going to have your agent buddy making your life easier running your data centers.
Can my agent buddy's paycheck go to my bank account? I'm okay with that,
that's
right?
Correct.
So, okay.
Yeah, that's why you'll sell the paycheck.
That's a deal. Okay. Yeah. Surendra, is there anything that is changing in terms of, I want to get later into scale across and, Jericho and things like that, not to kind of broadcom you, but...
I want to add to the front-end discussion that you
asked,
go ahead. Right? Is that, so training, million GPUs, 100,000 GPUs has been growing up. But if you look at the forecast, inference is picking up a lot. Actually, pretty soon, even now, inference GPUs are overtaking the training GPUs, and year or two out, inference is going to be even higher. So if you look at the back-end bandwidth versus the front-end bandwidth, there's a difference ratio for training versus inference. And there's a prefill and decode that Ram talked about earlier. So different people deploy different way. We work with multiple customers at Broadcom. But what I see is that many of them are deploying it as there's a prefill cluster, there's a decode cluster, and they're connected to front end actually. So the front end network is becoming more important. So the tokens that's generated, the states that are generated, moves over the front end network to the other cluster. The other thing I'm seeing is that I'm seeing a set of customers that are seeing that, okay, there's forecasting huge increase in the front end, still less than the back end bandwidth, but that's coming from the video generation. If you have used VO3, Google's VO3, it generates few small, short video clips that is like 50 megabytes or 70 megabytes. And the usage is going up. People generate voice easily, they generate cartoons, storybooks. So front end definitely picking up. Ratio-wise, it's still there, but still the growth is very fast on the front end side right now.
Cool, thank you. So last time when we met, Manoj, to your point, we all agreed on scale in, scale up, scale out. I put something on the social media saying that, hey, at least both of us agree. And since then, there are other academia joined and, started discussing. And scale across has come now, which is kind of carving it out of scale out in one sense, because distributed training is happening for some time, even though the clock of change is every 3 months now. So scale across is coming out of that. And I'm going to attribute scale beyond to Surendra. He forgot about it. But a couple of weeks ago at AI Infra Summit over lunch, Ram, it's not scale across, but Surendra coined scale beyond. He also said something about subsea and underwater, but that is for the next 3 months event, right? So let's jump on to scale across, right? Do you see scale across emerging out of scale out? And maybe we'll go in the same, right?
I think it is a natural progression right now, just because of the way we want to increase the clusters and what you have available within a given region. So just to establish that terminology, right? I mean, you have a hall in which you have a certain number of rows and racks, and that you have the power delivered. That puts a limit on how much you can put it there. That if you have multiple such hall makes a building, multiple buildings connected makes it a region. So there is a limit to which how much we can achieve there. And so you're going to find regions being created where the power is available and how the power is available. And if I want to make that bigger cluster work, which goes beyond 100K, then you're looking at widening circles of connectivity that is required. Today, they may be somewhere around 5 kilometer to 10 kilometer. But if you just lay out the way the powers and data centers coming up, we can easily see that going up to 100 kilometers. Now, this creates interesting problems for networking, especially for when you're trying to run such a higher bandwidth. And if you look at scale out has traditionally been large amount of RDMA use cases or InfiniBand use cases. When you're trying to scale it to that kind of distances, it brings interesting problems. Each of these technology from networking perspective, since we are at a key site event, brings up unique problems. Scale-in has a different problem, scale-up has and all of these are evolving by themselves. The scaling continues to evolve because as we start putting more and more dies into a single package, because that's how we are going to scale, has a different set of physical problems that we have. Scale up actually is an interesting problem where we are going to see scale up also going to increase, because as scale up has almost quadratic relation to scale out how much infrastructure I need, which means I put scale up infrastructure more, I can perhaps optimize scale out. So scale up is increasing. We are going to see, traditionally used to be only 8 GPUs in a scale up. There GB200, GB300 has put into like around 72 GPUs in a rack. That's a scale up network for it. We are going to see much larger numbers, which at that bandwidth increasing, the total rack bandwidth and rack capacity is going to become pod capacity or cluster capacity. So scale up is an amazing area of innovation there. Scale out, as we start trying to grow into that kind of a large distance, so when I look at scale out and scale across, I think there is a line blurring, but I think it's right to point out because those problems are not solved today. They're getting solved. So I think from that perspective, calling it out, saying that, hey, these are different problems because these are going to require products and technology solutions.
Joe, I mean, he talked about RDMA, right? Rocky across long distance is a completely different kind of science. We are only getting started with it, right? What is your perspective? Do you see them separating? Is there a good boundary between them?
So you got two things going here. One is bandwidth and one is latency.
Yeah.
And As you go out in these concentric rings, the latency obviously goes up just due to physical latency. It also tends to go up due to the complexity of the packet processing you want to do the outer rings. You want to do more packet processing and more complex forwarding decisions, typically. The other thing you have working here is, so if I scale a cost network, as I add tiers, I get exponential increase in the number of switches I need, right? For a given radix, and radix is king. If I do scale across plus scale out, or even front end, and I go, well, do I take a subset? I can't do arbitrary sets of things across clusters, so now there becomes a locality of GPUs that's important, okay? And that becomes critical. Moreover, if I'm really serious about scale across and I'm really serious about silicon diversity and heterogeneity, I need common protocols and common algorithms. So you're like, well, I can do whatever I need to do without UEC. Yeah, but it's not done in a common way. It's done in 5 different ways today. And that's fine up to a point because it solves the problem. Why do I need something like UEC, or why do I need scale-up standards? Because when I go heterogeneous, I'm going to have to solve the problem in an interoperable way. So do I have a latency problem or a bandwidth problem in each of these scales is another question to ask. I'm not going to answer that right now, but that's something to think about. And does that vary based on the kind of job? So training, everyone would say, is bandwidth bound. We heard that multiple times this morning. Inferencing might or might not be bandwidth bound. Maybe there's latency bound aspects to inferencing. If I have certain HPC applications, traditionally they were latency bound. InfiniBand was king in HPC for a very long time, and you can argue it still is because it's latency bound. There are a lot of small messages and a sync barrier that need to be correlated and consolidated across a set of infrastructure before you can take the next step. That's a latency problem. So scale beyond will have extreme latencies, but they might have high bandwidth. When I do scale across, I have all these clusters. How much connectivity am I going to have between the clusters, and how do I organize that connectivity? If I just have one giant cluster that happens to be distributed, that's certainly one way, but now number of switches and complexity to operate goes exponential. That's going to cause some interesting design points when you start talking about scale across. 25 years ago, metro clusters for storage networking hit the same thing. And there were a lot of metro clusters doing sync replication. And they all hit this same trade-off between the local data center storage network connectivity and the metro connectivity, and then the WAN connectivity for doing backup. Same problem is going to repeat here, same set of considerations. So it's, it's kind of an interesting way to look at what you do with each of these networks and their properties and how that all fits together. And then if you're going to try to operate, again, I'm going to come back to, you're going to need help operating this thing at scale. 100,000 GPUs. When you go to 1 million GPUs in a cluster that can handle multiple workloads and multiple users at the same time, whether they're, again, internal or external users, doesn't matter, you're going to have to be able to deal with that complexity somehow. You're not going to be able to hire enough people. Anyway, I probably went on a little longer than I should have. But,
no, but it's good, right? Because we are walking through this is something to establish the baseline, right?
Yeah.
You have Jericho 2, Surendra? Not 2, it's 4. I'm remembering my, going back to my Broadcom days. Jericho 4 now, is it directly targeted at scale across? Do you see that as a, Ram talked about specialized hardware emerging for these domains, or do you see it as a generic problem that you're solving?
Joe was talking about management. A lot of other things comes in, and the good news is it's all Ethernet. Right? It's like scale across Jericho that you're talking about. It's all Ethernet, standard Ethernet, standard monitoring, management happens. But Jericho is actually already proven for long distance storage RDMA networks. If you guys are interested, I can share with Venkat. He can send out, like, there's a 3-4 years ago, Microsoft published a paper on how they're running RDMA using Jericho across 40 kilometers. Of course, now the requirements have gone up to 100 kilometers, but Jericho is designed. So what I mean is, like, even 4 or 5 years ago, it's already deployed, working across 40 kilometers, and it can work at 100 kilometers as well. So as you said, like, Jericho is designed for that, to be able to drive very long distances. The thing about scale across is that you need very high utilization of the link, because these links are very, very expensive. You should be able to operate on fewer fibers, and you should have security as well, because if you have links that are crossing across 100 kilometers, you don't want somebody to be able to go tap them. The probability of that goes up versus you have something in the scale-up domain. So Jericho, as you are indicating, it has all those properties. It has the property of security is there. It has the ability to drive 100 kilometers is there. Same management of Ethernet management is there. It is designed for very high throughput. So Jericho also supports what is called a fat pipe, which is like 3.2 terabits, which allows you to get very high utilization on that.
Is it multiple links connected into, they appear as if it is one link? Yes. Maybe you can just define that a little bit.
The fat pipe is a technology where you can have multiple links across a data center, which is very, very common actually. Like, you have, let's say, 10 data centers. Like, you have a bundle of, let's say, 4 800 gig links that are going across. These 4 800 gig will look like one pipe. So let's say if you have multiple of them, you can group them in bunches of 3.2 terabits. And it looks like that one, even from the operating system and routing point of view and everything, it looks like a 3.2 terabit per second pipe.
So while we are at it, maybe you can touch upon a little bit on the protocol side of it, right? Broadcom has come out with scale-up Ethernet, still Ethernet. So standards versus, do you see, UA-Link and, multiple protocols that are kind of, being discussed, right? Any thoughts on how you see scale? I mean, SUE versus UA-Link versus Ultra Ethernet?
No, there is no, between Ultra Ethernet and SUE, there isn't as much difference.
Yeah.
The SUE is a way to get something out early. Broadcom is contributing the spec. Broadcom is giving out the spec, and then also like a design. And for closed customers, there's even IP that's available. It's just a way to get there very quickly. But Broadcom is working with Ultra Ethernet, and there's a work going on to standardize scale-up Ethernet. So there's no difference between. I see this more like a quick to the market versus like a longer-term standardizing. But with UA-Link, though, there is a difference. It's the same PHY, but the transport protocol is different. But I think whenever you bring something new, there has to be a good reason why that it exists. In my opinion, I think probably that's may represent Broadcom as well. There's no good reason for UA-Link as such. In sense, there's a latency is one of the reasons, but already Broadcom has the Tomahawk Ultra, which has 250 nanosecond latency. So it's a debate, but of course, market will settle it. But I'm expecting that Ethernet is the one that is going to prevail.
Cool. Going to switch the context, go back to another thing Ram mentioned, heterogeneous systems. How do you deal with it? Usually you have a very tightly integrated, your own custom, I wouldn't say minimalist, maybe you have to redefine that word for me, because less functionality is better. Then when you see all these heterogeneous systems out there where people are trying all combinations, how do you think about it?
So the AI infrastructure has been for some time now quite homogeneous.
Yeah.
Right. You define the whole cluster, and then it works like that. Of course, you have one large vendor. Of course, that drives a significant part of market share there, right? So that by that logic, it is. But even within then, you will see silos of infrastructure. You'll have one generation and another generation, and you create clusters. If you just look at how this thing progresses from left to the right or scale into the scale out and across, you will see that the homogeneity starts thinning down and starts becoming heterogeneous. So having said that, AI clusters tend to be managed very homogeneously today. There is a need for heterogeneity happening because otherwise, as we go to these larger numbers, there's a potential for a lot of siloed infrastructure, which basically leaves the capability to build the jobs across large number of GPUs becomes very difficult. But we are where we are right now. It tends to be very homogeneous. Even you will see that actually you will form the network clusters, which are extremely homogeneous. We talk about RDMA being standard, but there are so many different standards in RDMA, right? I mean, you are saying this feature will work with another. So there are various levels of pain points we are going to get into. We're not there yet, but I think that's the traditional direction. If you go to 100 kilometers of where GPU is being connected, it's very difficult to find all of them are exactly same. And we are going to have at least 2 generations of GPU, 2 generations of networks in there. So I think the heterogeneity will become a challenge from that perspective. Up to scale up tends to be very homogeneous. Scaling is for sure homogeneous.
Mainly because more synchronous system, more tightly coupled, or
Because the
reason?
functionality requires significantly defined inside the GPU, right? And this is where I think slowly the scale up, it used to be inside the system. You put stuff inside and the GPUs to talk to each other, that's the scale up. Now you're getting outside on the rack. So you're going to sit multiple switches. To Ram's point now, to your point right now, once you get it out, you got switches sitting there. The question is basically, this is where Ethernet normally thrives. That actually you have something that actually can be connected with standard cable. My services are growing at a speed that I need, and the whole ecosystem works without fail. I don't have to worry whether I got exactly same cable that is. So I think this is where Ethernet has a potential to play scale up, which didn't have it in the past. I think now looking at a rack and beyond rack in scale up, but scale out onwards, it's pretty much Ethernet and maybe InfiniBand, but it's really Ethernet in that infrastructure end.
Joe, do you see these requirements, right? I'll give you one example, right? Maybe you can correct me, right? Meta is using additional CPUs because you wanted to do a lot more pre-processing. So that's a customization of a standard rack. I mean, next to Jeep, right? I mean, even with NVIDIA. Do you see like your customers asking for heterogeneous racks? Maybe they're all homogeneous, but each customer asking for something slightly different? Or?
So it depends. So heterogeneous has multiple meanings. So heterogeneous can mean I want to use 2 different vendor switches, again, at any of these scales, with my homogeneous set of endpoints, GPUs and or CPUs. Heterogeneous can mean I want to mix and match GPU platforms. Heterogeneous can mean I want to mix and match the type of CPU system versus the type of GPU system. So when we say heterogeneous, heterogeneous itself is heterogeneous in that you could imagine worlds where different vendors' GPUs can work on the same training or inferencing job. You could imagine a world where that isn't the case, but you have multiple flavors of GPUs, to the earlier point of you have to do a collection of different things to make your whole system work. You can be heterogeneous in your connectivity vendors as long as you have a standard protocol and everybody obeys it, which is the point of having standards in the first place. At what scale do you need which kind of heterogeneity? I don't know that answer. I'm not going to tell you what that answer is. What I'm saying is that's a critical question for the industry to begin to answer.
But at least we are, there is not a single fully vertically integrated everything versus there is.
Well, at what scale?
Yeah.
So today we have vertically integrated systems.
Which is good.
I mean, we sell a ton of them. You can look in
but
the
do you
industry,
see a variation
press
of
releases.
those? Do you have multiple racks, each rack with a different combination?
We sell scalable units and even entire data center floors that are essentially a homogeneous architecture and approach. Okay, but we see requests for different ratios of GPU to CPU, different ratios of GPU to storage. The trend for different kinds of GPUs, I believe, is real and coming. That was highlighted earlier. That's coming. On scale up, it's all homogeneous today. Insider systems are now at the rack level where those exist. NVL72 racks exist in the world and have been deployed, and they work. What happens next in that world is maybe the rack is all the same GPUs, but now I can swap out the switches if I move to a standards-based approach, whichever one comes out. And I'm not going to make any statement in any direction on that because that's a complicated subject itself. Scale out, the same thing. You tend to see homogeneous GPU sets across chunks of racks connected through scale out. At scale across, maybe you start to see some difference, but can I run an AI job across, let's just pick the to main vendors, AMD and NVIDIA? Can I run a single AI job across those? Some jobs you kind of can, some jobs you can't really today. So where does that go? And do I standardize things at the GPU API level such that I can do that? But is the difference in the GPU capabilities mitigate against that, again, for a single workload? If I have different workloads, I have different segments that have different types of GPUs and different vendors' GPUs, that's all good. It's a really complex question. And I don't know what are you guys deploying like all different kinds of things for all different roles? And then you have now a big diverse infrastructure that you have to manage in a bunch of different ways?
So depending on, of course, sourcing capability, we need to source multiple things. Correct, right? They tend to come up with their own, like you said, scale-up infrastructure. Going to be homogeneous today, for sure. Because that has a GPU component in it, because GPUs are going to talk over it. Just a neat on the terminology, even though it is NVSO, which calls scale out, in reality it is scale up. I just don't like the wording, but it is scale up. But so that is true. The heterogeneous workloads across such infrastructure from job perspective, that is definitely going to be first step that perhaps can be targeted. Whether it's achieved or not, as you said, it's a mixed bag right now. But even at the infrastructure level, heterogeneity will start becoming a challenge because the way we will put the switching infrastructure, NICs, the cables, all of these basically are the protocols. They are going to become problem, even though they are not today. But the moment we go across scale out to larger scale, I would expect that to happen. And by the way, it doesn't have to be between GPUs. Even two NICs can't talk to you. Even the same NIC with two generations may not be able to talk to each other with the capability. So I think this is something that in a rush that we are in right now, like we said, 3 months, so many things happen. We really can't wait for all the standardizations and stuff to happen to be interoperable. That's true. But then there is always a desire that we'll interoperate. So it's going to be
moving
a tough
on,
problem.
in the interest of time, moving on to the another thing Ram and Joachim talked about, right? Specialized GPUs. You have, of course, inferencing and training got separated. Now prefill and decode. Do you see anything further? And what about verticals, right? For you, do you see each of your applications, right? I know we have accelerators for video and other things separated, but do you see anything going on in the verticals also? Or?
So there is a lot beyond meta infrastructure that I am not aware of, right? So you talked about multiple things that I'm aware of, but not understand, don't have knowledge about how to build. Within the infrastructure that we'll see at a hyperscale level, there was something that was separating out all of these accelerators before. Then they started collapsing, saying that I want to have a common infrastructure, but it's very difficult to maintain siloed infrastructure for different use cases like inference and then video encoding decode. They collapsed actually. Now it's possible that actually if the TCO justifies it, but normally hyperscalers like to collapse the SKUs if you can. But it's possible if the TCO justifies it.
But is it that just traditional, if you're central, then you go to distributed to central? Do you see that? Or is like you feel that over a period we'll have to have something?
There's too much stuff to ever go back to everything runs in one spot. I mean, okay, unless you say, well, that one spot is now the rack or the row. Okay, but that's not really one spot anymore. I mean, I think things have permanently crossed it's going to be disaggregated, and it's going to need heavy networking, lots of bandwidth, and complexity, and lots of protocols to control those traffic flows. I think we've crossed that divide, and we're never going back, personally.
Yeah.
So I think on the domain-specific accelerators, right? So within a data center, maybe they may be homogeneous, they may not be as much variety, but there's going to be many, many types of accelerators coming up. Just like prefill and decode is different. Actually, you guys, like a lot of money right now, even today, it doesn't come from these LLMs. It comes from the recommendation models. And recommendation models, the way they use the compute and memory and network bandwidth is very different, actually. There's spiderweb charts. If you go see, each one of these workloads some of them require a lot of network bandwidth. Some of them require very low latency network, but not very high bandwidth. So there's like you talked about SIM earlier, right? Like, so there's going to be something that's towards robotics. There's going to be something that's towards recommendation model. There's something for video generation. So when I talk to our customers, .com has a wide variety of customers. There are people actually that are like, you can call them, I think, semi-analysis calls them next-gen cloud providers, next-gen AI cloud providers. There are people who are specializing in these narrow segments. And there are a number of XPU startups and established people that are generating XPUs that are specific to these domain-specific architectures.
Yeah, so is the thing that fine-tunes and updates the LLM as you go the same as the thing that does the output processing to interact with a person? And is that the same thing that does the evaluation of the system state, where system is defined as all the things you're looking at with that AI application? Are those all the same? And if they're not, you're going to be heterogeneous in that way, guaranteed. And I don't think they are. Do you guys think that they're going to be the same?
No, I think across different use cases, you will see the heterogeneity for sure. But then you look at the overall spend and overall use cases and what I need, and then you'll see, okay, within that, what's my decision making? That's really how it is.
But isn't it true that a use case in an AI application will not be one thing going forward? That the future of AI, especially the speakers earlier, all the speakers earlier pointed to a world where a given application use case isn't one thing anymore. It's 5 or 8 or 100 different things underneath the covers. And it looks like it's one thing because it's talking to you about running your infrastructure, or it's talking to you about how to plan your vacation. But underneath the cover, it's a many different things. That was highlighted by all of the gentlemen who spoke earlier. And that future, this hierarchy of infrastructure to support that future means we'll all stay employed for a long time, but...
Yeah.
And we'll jump onto composability. Is composability coming our way? I know we talk about in a subdomain, like memory side of things and CXL, and you disaggregate and you aggregate in pools of one specific component. But do you see composability at the level of GPUs and heterogeneous GPU farms, and will compose at a next level? I don't know whether it will be at scale-up level or scale-out level, right, yet. But are you seeing that? Maybe we'll start with Manoj.
So again, general purpose compute and AI, they have separated out for some time, the infrastructure perspective. General purpose compute, we have seen that how do we really create more optimal utilization of the platform. There the composability has been playing a role or has been exploring. People have looked at how to do that, especially in the memory area. The storage has been separated or disaggregated from the compute already, at least for most of the hyperscale infrastructure, right? And so the composability from the job perspective, how much storage and what kind of storage, that exists. On the AI side, though, it is still not that, the composability is at a job level. Job level, what resources I can get and where do I get it from, there is a composability from that. Even if you say, hey, there is a 72 GPU in the rack, necessarily, it's not that necessary that actually I will use all the 72 GPUs. I may use small percentage for a different use case and what capabilities we have. But from a component level composability for the AI, that's TBD still.
Okay. Maybe we should open up for questions, right?
Yeah.
Couple of questions.
Yeah, or reactions. You're like, you guys are crazy. What are you up there talking
Do we have a mic over there? Maybe you could state your name and where you are from, and then the question, that will help.
Hello, Mark Butterworth. I'm actually a YouTuber. I'm trying to learn all about this AI hardware stuff to educate people. And what I don't understand is I understand that the scale up, but I don't understand the scale of it. So let's say here in Santa Clara, we're building a whole bunch of data centers. So what does one data center do? How many GPUs could one data center in Santa Clara provide?
Depends on the power you have, right? I'll give you an example. Let's say I have a data hall which has a bunch of rows with each one of them rack units. That's how we look at the infrastructure. Traditionally, rack would have been defined with like 11 to 12 kilowatts. Depends actually, different hyperscalers do different math. So if you say 11 kilowatt, based on the number of rows I can land in the data center, there is a power that is divided for what goes to the row, what goes to that hall. What changed with GPU is basically you got 8 GPUs basically that take up significant amount of power, which the whole rack can, in the past, DGX, if let's say you take a system, you can't put 72 CPUs, you will put only 8 GPUs, 16 GPUs. And that basically tells your whole data hall how much it can support. So the traditional number that we had seen was for Meta, that it was around 2,000 to 4,000 GPUs in a data hall. There is an interesting image, I think semi-analysis or somebody had published, that if you take a picture of and say that, what is the area utilized by the actual hardware versus how much is the white space, you will see the moment AI data center will see a lot of white space in it. The traditional data centers, the way they are used. So most of the traditional data centers are used for space which required for storage or anything that requires, but AI is really very concentrated use of power. So power is the really driving use case. The networking is the next, because networking is what is going to define how much bandwidth that I need to put for scale-up bandwidth or scale-out bandwidth, especially for scale-out. That if you have already infrastructure that was providing certain amount of bandwidth, then you're going to start diverting more bandwidth to that particular rack. Again, that will reduce the number of racks you can use. But primary driving is power.
So now I'm confused as always. So if I have 3,000, maybe 5,000 GPUs in a data center, how do I
Data hall, yeah.
Data hall. How do I get to 100K, 1 million? How do I do that?
I wish I had my pictures, but data center has multiple halls. So within data center, again, just making up a number for Meta, around 20 to 24K. And then you'll have multiple such building, what we call as a region, which is within a kilometer, which will basically form a region which has a predictable latency and certain high bandwidth. That takes you to around 100K. But you can't get to 1 million with it. That's why you need to go to the larger distance.
So physically, your reach for local networking, so just switch to switch, you can go, a kilometer fairly easily. That lets you then build a campus that's full of buildings that each house, let's say 16 to 64,000 GPUs. And now if I can put those in a couple of kilometer campus, and remember I have a kilometer reach from my top of rack to my spine, and then I have another kilometer reach from my spine to my super spine, and kilometer is just a rough number. So now I can do a fairly good sized radius, arrange all my buildings in a circle, put my central networking in the middle, and now I can hit my 100,000 scale. And whether it's a line and the buildings are in the center, whether it's a circle and the buildings are, doesn't really matter. But I can sort of hit those numbers. Now, if I'm building GPU clusters that individually don't need to be that large, but I want to be able to use some from over there some of the time, now we're talking the scale across. And that some from over there some of the time. So let's say I built 8,000 GPU chunks out of a few rows. And I have many of those buildings in a metro area, and I had a cross connect that was configurable, and I don't use it all the time. I only use it when I need some from over there because my current job is bigger than what one chunk can handle. Now you can hit those scales as well in a different way. So there are a lot of ways to hit the scale you're talking about, and all of the power and cooling densities are going up. Rack technology is a hot area of investigation. You can go look at our website or other people's websites and find out all about power and cooling. And so that's increasing the density, which increases the scale again. So it's a whole bunch of different fronts all at once, but you can hit these scales, and we have real deployments at these scales. The most prominent one that's completely public is the X.AI scale, and if you go read up on that, you'll see the scales and densities that are hit. And again, that's the most prominent public one that I can just say, go look it up because there's press about it.
All right, thank you.
Cool. Thank you.
That concludes our final episode of AI Unboxed. Today's panel shared real-world insights from Meta, Broadcom, and Dell on scaling AI data center infrastructure to optimize performance and efficiency. We discussed practical lessons around architecture, networking, and system-level design that are critical to deploying AI at scale. And we hope you found these insights helpful as you plan your own AI infrastructure decisions. I'm seeing some great questions coming through in the chat. We may not be able to get to all of them live today, but as always, our experts will follow up with you by email. Thank you for joining us.